So then allow me please to introduce Ambrogio Fasoli. Ambrogio Fasoli is the program manager of EUROfusion, the European Consortium for the Development of Fusion Energy, and a lecturer at EPFL in Switzerland, in Lausanne. So Ambrogio, thank you very much for joining us today. And please, the floor is yours for the presentation.
The group, I was in the chair in the academic council the first years of FuseNet, and I really support this initiative, and I completely echo Roddy's words that if there is one thing that all of us can say we do, it's fusion relevant, is to try and bring people from the younger generation in and talk to them and try to pass some of our knowledge, but also to learn from you. The pleasure of teaching is always to learn from the students rather than the other way around. So let me try to give you a bit our vision from EUROfusion, what we are doing and what we should do to advance the roadmap. In other words, to go towards the power plant, which ultimately is our goal. I like to put things a little bit in the context because I'm not sure all of you are totally familiar with fusion. So let me just introduce what we're doing in the very general physics-based sense without any equation, nevertheless. So as you know, if you consider all the elements and the nuclei of the elements, the energy that you have per particle in the nucleus, per nucleon, is not the same, and for the different atomic numbers, for the different masses of the nuclei. And the reason is that, of course, the rearrangement of the nuclei depends on the neutron force and so on. And this is why you can move along this curve. And moving along the curve means that you don't move along a flat curve, but you move along a curve that is going down from left to right and going down from right to left. Going down to what? Going down to the most stable nucleus in the center, which is iron. So you can split a big nucleus and go down in this curve, which means you have energy in surplus that is released, and that's nuclear fission. Or you can actually do the opposite, which means combining small nuclei and yet go down in this curve again, which means, again, releasing energy. Another way to say is that the end products of your reaction will be slightly lighter in terms of mass than the sum of the product that you begin with, which means you have a mass that's available to be transformed into energy by E equals mc squared. So this going left to right is obviously nuclear fusion, which is even more efficient in terms of a mass transforming into energy, because this curve is steeper. So you have a even higher energy content in a fusion fuel than you have in a fission fuel. And on top of that, of course, you don't split nuclei that are heavy and radioactive and forming nuclei that are still radioactive and still relatively heavy, but you do the opposite. You use very small nuclei, the nuclei of a hydrogen or its isotopes, and form a helium nucleus, an alpha particle, and a neutron. Because now I'm looking at a specific fusion reaction that we are actually looking at producing in our program in Europe, which is DT. Now that necessitates, of course, very high temperatures because the nuclei don't like each other, repel, and despite the tunneling effect, thanks to quantum mechanics, you still need to reach temperatures of the order of 10, 20 keV, which means hundreds of millions of degrees, at which temperatures you only have plasma, which is a state of matter that's pretty exotic on Earth, but is actually the one characterizing the rest of the universe that we know of. Most of the universe that we know of is made of plasma. The stars are all plasma, and the interstellar matter is in the form of plasma, and so on and so forth. Now, we work with plasma because we want to achieve fusion, and therefore plasma physics and fusion are intrinsically related. I say we use the DT reaction because it's by far the easiest of all, which means the highest probability at decent temperatures, higher cross-section. And where do we get the fuel from? Well, where deuterium exists in the water everywhere, and there's a lot of it. Tritium doesn't exist in nature. We only have a few tens of kilos on Earth because of cosmic rays and some other activities that we shouldn't have done. but this is far insufficient. So we had to produce tritium in situ, and we do that by taking advantage of the fact that the neutron that comes out from the fusion reaction itself can react with the lithium, in particular lithium-6, that will be put around the plasma that forms the core of a reactor, and by reacting with lithium-6 produces a tritium nucleus, which is then reinjected. Tritium is produced in situ, is not taken from outside, and it's not rejected to the outside world, which is very important because tritium is radioactive. Of course, the neutron also provides the heat to produce electricity, and the other byproduct of the fusion reaction is the helium particle, the helium nucleus, alpha particle, which will contribute to the self-heating of the plasma. Now, the approach that we take in Europe is mostly based on magnetic confinement. We, of course, cannot use gravitational confinement as the stars do. But at the moment, we don't consider in our EUROfusion program as a mainstream approach the one on inertial confinement, which is based on having mini implosions and mini pellets that reach very, very high densities and don't necessitate a high confinement time. In fact, the confinement time is very short. The product of the two is what counts, so this is still possible. But we do that. We obtain that product in magnetic confinement, taking advantage of the plasma, of course, is made of charged particles, by having a relatively low density, so 100,000 times less dense than the air we breathe, but holding the plasma and its energy in a space that we allocate to it for a macroscopic time. So that's what we are doing. To achieve that, we have two ways primarily. You need to have a cage that has some sort of a helical twist to it, a cage made of magnetic field lines. And we can have this helical twist either by having the twist in the coils themselves, they produce the field. This is the stellarator, it's a very promising avenue. Or by having the twist with a combination of external coils and currents in the plasma, which is the concept of tokamak, which at the moment is even more promising because the parameters that have been reached are about 60 times higher in terms of the fusion performance for the amount of density you can confine, how long you can confine it for, and the temperature that you achieve. Now, Dario said that we need, and Roddy said that we need all of you. We need all of you in a number of disciplines. This is a very crucial message that I want to pass. We need physicists, we need engineers of all kinds, we need data scientists, we need artificial intelligence experts. I mentioned a few elements that are fundamental in what we need. For example, we need understanding the physics and understanding how we can simulate what's going on in the complex plasma in our tokamak or stellarator devices. Why is it complex, actually? Well, because it's very intrinsically nonlinear. The plasma is a source of electromagnetic field and is a victim of electromagnetic field. So this loop is already in itself a very interesting and very challenging situation to be in physics. The plasma is characterized by collective effects at very many scales. And these extensional scales makes it extremely challenging for also the numerical simulations. You have to go from the plasma particle orbits, which are on millimeter scales and on in terms of times of a nanosecond scale, to then a gigantic mass, which is for example, in ITER, the plasma is in the order of 1,000 cubic meters of size, and the intrinsic times can be minutes. So you can see the span of the scales there. It makes it very challenging even for the most advanced supercomputers. The plasma is complex, has a complex geometry because it's not a fundamental physics experiment we want to do, but a reactor. And so it has to be following the constraints from engineering. The plasma is intrinsically anisotropic because you have magnetic fields and because of this complex geometry. And the plasma is intrinsically turbulent. You have a lot of gradients in the plasma. You have one of the hottest places in the universe in the center of the plasma, and a meter away or so, we have one of the coldest places in the universe because we have to cool our superconducting coils to almost absolute zero. And the edge of the plasma is, of course, much colder than the core of the plasma, even staying within the plasma. So that generates a lot of turbulence we need to understand, we need to predict, and possibly we even need to tame. The plasma is characterized by multi-physics features because in the core is fully ionized, so it's a pure, again, plasma physics object, if you like. But as you move to the edge, you have neutral atoms, you have impurities, you have radiation, you have interaction with solid surfaces, and so on. You also have in the plasma elements that are produced by the fusion reactions, as I mentioned before, alpha particles, for example, that are non-thermal, that don't belong to a thermodynamic equilibrium. So it's very challenging physics of different kinds. And the even more interesting point, even more challenging point than all of these individual elements that I mentioned is that everything has to work together. So the key word for me in fusion is integration. I try to visualize that with a movie. I don't know if you can see it. Hopefully, yes. This is a movie that has all the particle orbits calculated actually with a realistic code inside the tokamak. And you can see that we need the core, which is very nice behavior in terms of confinement. But we also need to extract the particles and the power once they are used. So we need an exhaust concept. We need to pump out. We need to inject the fuel. We need to control it. We need to tame the interaction between the plasma and the wall. And the performance of the core has to be compatible with the performance at the edge and the performance of the layer in between and so on. So everything has to be integrated. And this is also to be integrated in a system of systems, which is the fusion power plant, which has to actually run in order to extract heat and then electricity and create and reinject the fuel and so on and so forth. All of this has to be integrated. And I think many of the proposals that we see around the world do not necessarily take into account this element. But we in Europe, in EUROfusion, we do. And that's a crucial element. And of course, ITER is the ultimate proof that integration is needed and integration needs to be demonstrated. Now, one may say at this point, okay, this is a fantastic set of physics and engineering challenges. Integration is a challenge that comes on top of all individual ones. Will it ever work? Well, yes. Yes. You can even hear it work now, because I'm projecting the movie of the record shot in the JET device, our European device, which has ceased operations after 40 years of successes, actually the end of last year. And this record shot obtained a record amount of energy in a plasma, 69 millions of joules. And to do that, he used about 0.2 milligrams of fuel, deuterium and tritium. If you had to obtain the same amount of energy with fossil fuels, you would have needed a few kilos versus a fraction of a milligram. This is also underlying how huge is the difference in energy density between the fusion fuel and the conventional fuels. We sustained that for several seconds. We sustained that in the conditions that are reactor relevant, with walls made of beryllium and tungsten. In particular, tungsten is a material that's going to be used for it and for the reactor. And the other thing that is important to underline is that this behavior of the plasma followed the predictions that we had. And in some areas of physics, you hope the predictions are not followed, because what you're after are novelties so that you can explore frontiers in knowledge. We do explore frontiers in knowledge, but with a goal, and the goal is a power plant. So whenever we have prediction that is followed by what the plasma does in reality, actually we are happy, because it means we can keep it under control and eventually we can extract energy from it. Now, the next big experiment in our environment is, after JET, is ITER. ITER is the integrated proof of the scientific and technological feasibility of fusion. You will have a speech on ITER, so I will not dwell too much on it. I will only say that from all perspectives, ITER remains the most important milestone we have on the way to fusion. And is also one of the most ambitious things we ever had done as humankind. So the fact that there be some delays and some overspending is absolutely, I would say, natural. Now is actually almost completed in terms of assembly, and we are about to embark on a journey with it that's really crucial, because it will be the demonstration of a burning plasma regime in which the plasma will heat itself more than we heat from outside, is the bottleneck on the way to a power plant, to understand that and to control that. Yet, ITER is not the ultimate step, because we need to demonstrate not only that it's possible to have a fusion scientifically and technologically, but also that we can have a fusion reactor that can sell electricity for society. That's what we call the demo step. And this is where Europe is, in a sense, taking the lead, because we are pushing this demo step already now. What does demo do? Demo demonstrates the performance, the integration, and the availability of the key technologies for a power plant. Again, the word of integration here, but also the new word, availability, because this is not an experiment anymore. Now we're looking at something that we produce electricity 24 hours a day, 7 days a week, 365 days a year, and decades long. To produce electricity, you also need to produce its own fuel. And so we had to have a self-sufficient fuel cycle, which is not an easy thing to have, although the fusion reaction, the nuclear reaction with lithium is very easy to write, but the plant is not easy to make. And he has to produce a net electricity of over 300 megawatt to really make the demonstration final. And if you remember thermodynamics, to have an electricity output of about 300 megawatt, you need to have maybe about 3 times more thermal power, so of about a gigawatt of fusion power. And the length of the pulse that would be important to achieve so that we can really make the demonstration is about a couple of hours. We are looking at the conceptual design of them already, and this is one of the key activities of our consortium. What is our consortium? Our consortium is EUROfusion, which works on behalf of Euratom and European Commission to integrate research and development in fusion science and technology for all the continent. We have 26 member states of the European Union and 3 associate members, UK, Switzerland, and Norway. We have a couple of hundred research institutions and universities and 1,000 students associated, hopefully more and more, and a few thousand research staff and support staff. In EUROfusion, we have an allocation of resources, of course, to science and to technology, and to the fact that the barrier between the two is less and less important. So we really work in a comprehensive and, again, integrated way. And one of the things in the new management of EUROfusion, recent management we have done, is to increase the effort in training and education. As I said before, as Roddy said, as Dario said, this is absolutely crucial. So there's the need of new ways of students like you in many, many fields. We need, as you say in English, all hands on deck. We need experts in all areas. And don't worry, if you're not an expert, you become one. And in fusion, you become at the same time an expert in an area and a generalist, because you also need to have an overview of what's going on. And it's a very multidisciplinary environment, very multicultural, very integrated, also geopolitically and humanly. So it's an integration of the staff and of all the countries around. We actually need to work with China, Russia, United States, Korea, all together. In Europe, we work with all the European members, but also Ukraine, United Kingdom, Switzerland, etc. So integration at all levels is a key word once more. We realized that on the way to demo, we need to address a few gaps. So R&D is still needed. Those of you who are keen on R&D, don't worry, there's still a lot of work to do. There's still a lot of work to do on areas that we know what they are. This is the good news. So we know where to focus. We know we need to focus on tritium and blanket technologies, because this extraction of the energy and the creation of electricity, this the regeneration of the fuel and reinjection, in principle is relatively easy, but in practice is really complicated. We need to demonstrate it can be done in a reliable way and in an economically viable way. We need to develop the materials that are capable of withstanding the heat loads that we generate, which are gigantic, tens of megawatts per cubic meter. They need not to be too much activated by the neutrons that come out, and they need to be achievable in an industrial way at cost that can be compatible with the commercial deployment of fusion. It turns out that it not only is difficult to build materials, it is also difficult to test materials for fusion, because the fusion neutrons are very high energy, 14 MeV. And so we need to develop sources that produce that kind of neutron energy so that we can test the materials in relevant environment. But we are doing that. For example, we are building an accelerator-based source in Granada in the south of Spain, beautiful spot, by the way, where there will be the accelerator with the deuterium ions impinging on lithium liquid sheet to generate reactions that then produce neutrons with the right energy, which will then impinge on the test materials that we will expose so that we can qualify the materials. We also need to understand the concept of exhaust for plasma and power. We need to exhaust the plasma and power efficiently without affecting the confinement in the core. So we have it difficult. We had to almost perfectly confine the core, but not quite perfectly because some of the plasma has to be coming out. And at the edge, we have to suck this out so that is pumped out, but not affecting the core performance. So it's a very delicate challenge. We are progressing enormously there. We also progressing using elements like artificial intelligence and real-time control to optimize the whole scenario. We need to understand this, how to control the plasma also in the core and all elements. We need to understand how to tame the instabilities that can happen there. They're beautiful to watch at in a star, like in our own sun, but they're not something we want at the surface of our little star inside our tokamak, for example. We still need to clarify a few elements of safety and waste, and we need to develop robots because everything will be handled by robots in the future device, and in fact in ITER as well. So I have mentioned already a couple of points on the tritium. How do we want to accelerate the developments to demo? Because we do want to accelerate. And when I say we public entities in conjunction and in collaboration with the private investors and the private industry. I don't think in Europe we can totally outsource the business of fusion to private. Neither can I imagine that we can actually go towards a reactor only with universities and research centers. We need to combine the two things, and I will say a few words at the end of my speech about that. Obviously, we need to accelerate understanding and solving the gap areas that we have identified. We do that in synergy with the ITER baseline development. As you will hear from the ITER people, this has been just developed and is a very, very good approach with a tungsten wall so that there would be relevant data for the reactor immediately obtained in ITER. We're also exploiting our own machines in Europe, but also the largest tokamak in the world, which is now GT6 CSA in Japan, which is not a Japanese tokamak purely, but is also a European tokamak to some extent because it's been developed together. We need to increase our efforts in simulations for plasmas, but also for engineering. That's where we have the complete open door to innovation, including artificial intelligence. We cannot ignore the revolution there. We need to take advantage of it in our own areas. And I say areas plural because it's not just about controlling the plasma. It's also about optimizing the design of engineering pieces, optimizing the construction of them, optimizing the integration of all of them. One point that may sound boring and bureaucratic, but is actually crucial, is the licensing question. You need to license the nuclear plant that the fusion reactor is, and you need to do that in a relatively agile way, like other continents are doing, for example. And for demo, we also need to identify the site as soon as possible so that we can proceed with the development. Speaking of development, and this is a point that I made already 3 or 4 times, and Dario and Roddy have made already, is the development of the workforce is crucial. But not only the development, but the maintenance. In other words, you need to be formed, and you need to be finding a job. And at the moment, there are many opportunities in academia, in research centers, in industrial partners, in private startups. We need to do that at all levels and with all kinds of diversity being in front of our eyes every day. Diversity meaning diversity of background, diversity of geographical origin, diversity of genders, and diversity at all levels. We need to look at the mutually beneficial international collaboration. We are in a very privileged situation in Europe that in that we can have a dialogue with China, we can have a dialogue with the US, and we can collaborate with both parties. And they're all very interesting. They all have a very interesting fusion programs, which by the way, have very similar perspectives and the vision to ours, except ours is much more integrated. And we need to manage the human people, but also we need to manage the knowledge we already have, because we have built an immense amount of knowledge. For example, developing ITER, we need to document and maintain that so that it's not forgotten in a transgenerational effort that fusion is. We need to parallelize and take risk to some extent, because otherwise the sequential approach from a jet to ITER and demo will take us too long in time. We need to parallelize and we need to take some risk, but we need to do it in a reasonable way, ambitious but realistic. And we need to do that, as I said before, in partnership with between public and private, and in particular with industry. Our vision doesn't stop at demo necessarily. We also need to prepare the further ultimate step of power plants. And to that extent, we need to see what the stellarators can do. For example, we need to see further innovation elements like high temperature superconductors, advanced structural materials, and so on and so forth. So in a nutshell, we need everybody on board. We need all devices to contribute that we have and that we are developing to contribute to optimize the operation of ITER and to optimize the design of demo. And devices means not only plasma devices, but also a number of technological devices that address a number of problems that we still have on our way to the power plant. Thank you very much for your attention.
Ambrogio, thank you very much for this very complete and outstanding presentation. I think it was really nice to see the overview of what fusion is, and also all the initiatives that are being held in Europe at the moment from EUROfusion, all the interest in the field. And I have to say that I think we have come a long way from the very start of fusion. You have mentioned a lot about all the activities that are being doing, the construction phase of ITER. So I guess you agree with me that this is a very exciting time to be involved in fusion as a student, to start a career, because we have a lot of resources.
The most exciting ever. I wish I could restart now.
Happy to hear that, but yes, this is interesting times. We have a question from the audience. So the audience here is able to ask questions through the chat. So we have a question from Rick. So if you can name a few specific topics that need to be increased in simulation, some specific topics whose effort need to be increased in the simulation field.
Okay, two things come to mind. One is, allow me to use again the same word, integration. One is to bridge between the core of the plasma and the edge of the plasma. And I say that for simulation specifically because the core of the plasma is where the plasma is super hot, basically has no collisions, basically has no atomic physics, it's pure plasma physics. So you need to, but it's hot, so you need to have some sort of jet kinetic approach. Now, because of the orbits, we can simplify a little bit the dimensionality. We have so-called gyrokinetic rods, and they simulate pretty well the core of the plasma. On the other hand, the very edge of the plasma is relatively cold. It has a lot of collisions. You have even atomic species and even molecular species sometimes. And so it needs a different kind of approach in simulations, typically based on fluid. And the question is how to interface those two areas. I think the next frontier in simulation is really to put the two areas together and describe the interface between the two, which is crucial. The interface determines the performance on the core, and it determines the performance at the edge, and how the plasma is, for example, is detached from the plasma wall materials. With this detachment occurs when you have some recursion, if you like, between the plasma and the walls made of neutral. And the conditions for detachment to achieve and to maintain detachment are crucial. And so this interface between the two areas, I think, is the next frontier. But I mentioned another point for simulation, which is simulations for the engineering element. We need to simulate, for example, how the tritium bringing blanket works so that we can optimize the design, we can optimize the construction of it. At the moment, the concepts are too low technology readiness level to be deployed. We need to really increase that level, and we have to do that by simulating the different fluid dynamics elements, the different ways of building, and so on and so forth. So there are quite a few questions coming up. Let me try to catch up. What is your opinion on Stellarator versus tokamak? Stellarator has a huge potential because it doesn't have current, or at least not the current that we drive from outside. which means you have less kinds of instabilities. You don't have this possible difficulty in a tokamak, which is what we call disruption, where all of a sudden the current disappears and the plasma collapses. It has, of course, the complexity of the coils and the precision of the construction installation that are a little bit challenging. Then Einstein 7X, the largest accelerator, which is in Europe, in Germany, is now demonstrating a very nice set of performance achievements. We still need to demonstrate from the accelerator side that the performance can be that of the tokamaks. We're still a little bit away, and I'm sure eventually we'll do it. So we consider accelerator as a very good option for a power plant. For demo, our thinking at the moment is that because we want to go fast, the readiest concept is the tokamak. So my personal opinion is that demo will be a tokamak, but the power plant may be either.
That's good. I think we have a lot of questions. If you want, please choose one, and then the rest one maybe we can forward to you later.
Okay, you filter for me then. Okay.
Yes.
Please
So
let me know which one I should address.
Yeah, maybe the last one, if I may allow. Then perhaps if you can discuss more about tritium, because tritium, I think so what would be the main challenge regarding tritium?
As I said, the blanket. So I'm a plasma physicist, so I'm not super expert on tritium, but my understanding is the following: historically you have two concepts. One is based on water-cooled blanket, which means the water is circulating, and that's the one that extracts the heat. But water is corrosive, and so this is not easy. And you have a lot of pipes inside, tens of kilometers of pipes, lots of weldings, and this is the nuclear environment, very, very difficult. The other concept is based on helium as a coolant, which has other issues because we have not the experience of having such a big system cooled with helium. The lithium is in the form of ceramic pebbles, little stones, if you like, which is a combination of lithium and other materials. That has also its difficulties. Perhaps we should be open to combining the concept that we have, being completely open also to new redesign of things using artificial intelligence, using also additive manufacturing to build, because the manifolds in there are complicated. You have like a pressure water reactor from fission around, in terms of complexity, around a star, which is a tokamak or accelerator. So that's too complex. So maybe we can build something that is not based on many weldings, and is based on the path for the fluid to be just dictated by the three-dimensional elements that are built in there. Maybe we can use the same fluid that circulates through the plasma facing material and through the back part of the blanket. So we are looking at these innovative approaches, and we need to be having a dialogue with the nuclear fission experts, and that's another bridge we need to build and reinforce. So this is the challenge. The other challenge, which is incredible if you think about it, because it looks trivial, but it is not, is the recirculation of tritium. How much tritium we need on site depends on how fast we are in recirculating it. So the faster we are, the less tritium we need, which is important. And we have ideas how to make the recirculation of tritium, the purification of tritium to be reinjected in the tokamak more efficient. If we gain a factor 2 there, we gain a factor 2 in the tritium inventory, which we need on site, which is an incredible gain for the fusion economy. So yes, there are challenges, and these are the main elements I can identify.
Ambrogio, thank you very much. I think we'll keep the other questions for later. Maybe we'll see how we'll deal with them. But thank you very much for being here.
Thank you very much. It's my pleasure always to be in this community. See you soon.
See you soon. Thank you very much, Ambrogio.